we went from a global perspective to a local perspective. As far as solving mass and momentum equations are concerned. So, we wrote the mass and momentum equations in local form. Then we found that these have to be supplemented by a material behavior function called the constitutive relationship, which related stress to strain rate. So, specifically we considered a linear relation as applicable for Newtonian fluids, giving rise to viscosity as a material property. So, what does it give you? Mass momentum equations with the constitutive relationship for a Newtonian fluid. When you put them all together, what do you get? Navier-Stokes equations. We briefly talked about the mathematical properties of these equations. So, mainly we have looked at these equations in Cartesian and cylindrical coordinates. The full Navier-Stokes equations are hard to solve exactly, that is. I did mention that computational tools that look for approximate solutions of the full Navier-Stokes equations are very much being developed. But in the framework of analytical solutions, these are hard to solve, and we look for simplifications. Now, one class of problems where simplifications were applied dealt with steady incompressible flow. Then we required the flow to be fully developed We also looked at the low Reynolds number form of Navier-Stokes equations that give you Stokes equations. We looked at the solution for slow flow past a sphere. And the Stokes law of drag. Then we suddenly switched to the high Reynolds number limit. Giving rise to Euler equations, Kelvin's theorem, irrotational flow, and potential theory. So, this is the sequence in which we have progressed. What is Kelvin's theorem? The vorticity of a fluid element in inviscid flow is conserved, or it is a constant, and if the approach flow is uniform, then it is 0, under which you get irrotational flow. If omega is 0, Kelvin's theorem tells you d omega dt is 0, irrotational flow is omega equal to 0, based on which we developed potential theory. So, in the study of potential flow past objects, we encountered regions of favorable and adverse pressure gradients. Why did we have to look at the pressure gradient? Because we got a very unique result that potential theory can predict lift, but cannot predict drag. It predicts drag as 0, okay? Does not predict non-zero drag. It is correct for lift, it is also correct for moments, but not correct for drag. So, then we started looking at the pressure distribution. Why? Because lift and drag emerge from the pressure field. There are no shear stresses, mu is 0. So, we looked at the pressure distribution and we found that in the region of a favorable pressure gradient, the match between potential theory predictions and experiments is good. In regions of adverse pressure gradient, the match is poor. Specifically, pressure tends to become constant in a region of adverse pressure gradient. So, we compared nozzle, diffuser and a circular cylinder which has both adverse and favorable and adverse pressure gradients. So, to explain the departure of experiments from theory, we looked at the flow field in some more detail, giving rise to boundary layer theory. Where we found that there is a thin region very close to the wall where viscous effects are important, where vorticity is not 0. Outside that region, vorticity is 0. So, potential theory can be applied, but very close to the wall, potential theory cannot be used. But because the outer flow is potential, pressure distribution can be obtained from potential theory and applied throughout the boundary layer. This result helped us analyze favorable and adverse pressure gradients individually. So, we found the boundary layer to remain intact in regions of favorable pressure gradient, but for an adverse pressure gradient, the boundary layer separates from the surface of the object. Okay. So, we also saw that early separation will result in high drag, delayed separation will result in low drag. So, we started looking at means by which we could delay separation, all in the context of a circular cylinder. So, one approach was weaken the adverse pressure gradient on the rear side of the cylinder by elongating that region, giving rise to an aerofoil kind of a cross section. That will narrow the wake, delay separation, reduce drag. So, this gave us, so one approach was if you have this elongated surface, separation point may shift to point P and the size of the wake is quite narrow, which reduces drag. The other approach was to energize the boundary layer so that it overcomes a greater part of the adverse pressure gradient. So, we saw that if the boundary layer were to become naturally turbulent, then there is a delay in point of separation. You can also energize the boundary layer. One way of doing it is to trip the boundary layer using a disturbance. So, this is the original separated boundary layer. So, what I have shown, what is the line coming out? That is the boundary layer emerging from the solid surface. This is under laminar conditions, and if you either increase the Reynolds number so that the boundary layer becomes turbulent, or you disturb it in some manner, it will delay the point of separation. This is point P. I am always using this P for point of separation. To somewhere here. There is a delay in the point of separation when the boundary layer is energized, when it becomes turbulent, so that you have additional kinetic energy available inside the boundary layer to overcome adverse pressure gradient. The delay in the point of separation will lower force drag acting on the cylinder. So many of these observations, particularly of real fluid flows, were illustrated through videos and some slides. Now, just a small comment. Potential theory will hold outside the boundary layer, boundary layer theory will hold. So, this is the portion, boundary layer theory will hold inside boundary layers. Then what theory do you use in the wake? This is the wake. This wake is the disturbed region of the object. Okay. If the wake, if the disturbed region is small, then you know the laws of momentum in the fluid is great and forces are also large. That is one way of thinking about it. The other way of seeing it is that there is no pressure recovery, and therefore, the force, this loss of symmetry in pressure distribution leading to large forces and acting on the object. So, multiple explanations for the same phenomenon. What theory will you apply for describing the flow field in the wake of a cylinder? It is not low Reynolds number, it is not fully developed, it is changing all the time, it is not potential flow. Why? Because it is bounded, the wake is bounded by boundary layers where vorticity is produced. So, not potential theory, not boundary layer theory. So, what theory will you use for describing flow in the wake of a cylinder? You will use the full Navier-Stokes equations. Okay. So, we are not in a position to solve analytically the flow field in the wake of a cylinder, okay, but the applicable theory is Navier-Stokes. Okay. So, let us revisit those slides. So, I have shared these slides with you on email, right. In all these pictures, flow is from left to right, and it says increasing Reynolds number. So, in the first one, maybe I should have numbered them. That one is 1, that is 2 in terms of sequence, 3 and 4. So, that one is maybe a Reynolds number of around 20 or so, showing the formation of a recirculation, steady recirculation bubble. The boundary layers come out and they meet, boundary layers from each side will come out and meet, forming a, it's called a bubble. But when you increase the Reynolds numbers, these shear layers roll up. It's called a rolling up. This is a rolling up, and they detach from the surface of the cylinder. So, there was a video given to you where the vortices, what are these vortices? These are boundary layers emerging from the surface of the cylinder. They roll up and they are transported with the flow. Okay. These are boundary layers originating from the solid surface, and they are carried by the main flow at higher Reynolds numbers. Then just to illustrate the point of moving the point of separation. So, that is well, here it is a sphere, the same thing happens for a cylinder. Okay, I managed to get hold of a sphere quickly. So, I am just showing you a sphere. Okay, so, you can see that for laminar separation, that is, the boundary layer is laminar. You do not see the boundary layer, it is just too close to the surface of the object, but you can see a disturbed region. What is that stem? That stem is holding the sphere. Okay, there is flow going in, and then there is a stem holding the sphere. and then the stem is a right angle stem comes out. That is the wake region, which you can see spans the diameter of the sphere. So, the drag coefficient for the sphere is quite high, okay, compared to attached flow. So, you have to go back to CD versus RE curve, where you had this reduction and then constant. So, at that Reynolds number, if you had extrapolated this diminishing curve, you would have a very low drag coefficient for attached flow. But for separated flow, it is probably 2 orders of magnitude higher. Okay. Then, here instead of increasing Reynolds number, a trip wire is used to energize the boundary layer. So, the boundary layer becomes turbulent and the point of separation has come down, it is somewhere here, and the wake is much narrower. So, making the boundary layer turbulent delays the point of separation and lowers the drag acting on the sphere as well as the cylinder. So, if you remember CD versus RE, both sphere and cylinder, drag coefficient is constant like that, and then suddenly there is a dip. That dip is because in a natural setting there is no tripping. So, there is a sudden decrease, it is also called drag crisis, sudden reduction in the drag coefficient. So, this tripping shows that sudden reduction can be initiated at earlier Reynolds numbers also. Okay. The video given to you has momentum injection, which suddenly delays the point of separation. So, let us see if it runs. This is aerofoil cross section is one more method of delaying the point of separation. So, you have a longish section on the side of adverse pressure gradient. So, that the adverse pressure gradient is very weak and separation takes place much later. So, the wake is very narrow over there. Okay. This is with some slight increase in angle, the wake size has increased over there. So, these pictures are consistent with the discussions we have had. Now, let me attempt at playing the video. I do not remember which one. Is this the one? This you can see the boundary layer, it is sticking to it and there is a point of separation. So, this video just illustrates the point of separation. There was, no, this is formation, you have a boundary layer separating and rolling up. That was that video. This one, yeah, has that momentum injection. Yeah, you can see that boundary layer was separating, and then with a little bit of injection of fluid from the wall, suddenly it attaches to the wall. That is a delay in the point of separation, and hence a reduction in the wake size, reduction in the drag coefficient. Okay, so you will have to study these videos on your own separately and connect them with the theory that we have covered in the class. Okay, so I would say connect theory with slides and videos. Okay. So, in the first part of the course, we were always solving mass, momentum and energy equations. In the second part of the course, temperature was constant and we looked at just the mass and momentum equations. So, it is fair to ask what happened to the energy equation. So, let us take a look. You remember the control volume formulation. The foundation of the momentum equation is would be the Newton's laws of motion. Foundation of energy equation would be the first law of thermodynamics. What about the second law of thermodynamics? I will comment on it probably in the next class. So, you remember CV. So, the notation used is heat addition to the control volume is positive and work done by the material on the surroundings is positive. Okay. If there is a change in direction, you also have to change the sign. So, with that sign convention. So, here W dot S is shaft work, which is the work done by devices that are placed in the control volume. In global analysis, we looked at devices like pumps and turbines. We are aiming for local analysis. So, let us simplify this development. So, for local analysis, you are going to look at energy distribution at the small scale, and so there are no devices. So, the shaft work is 0. The definition of total energy is I plus P over rho plus U square over 2 plus G z. Okay. Now, this I plus P over rho is often called enthalpy and is written as specific heat for most fluids of the type that we have considered in the first part of this course, where we had air, water, oils. So, if you bring in compressibility, then it has to be specific heat at constant pressure. If it is incompressible, which is what we have done all the time, then C at constant pressure is equal to C at constant volume. So, it is just C. Okay. So, there is no need to put a suffix P, which comes in if the material were to be compressible. Okay. So, specific heat times temperature. Now, we could simplify the analysis a little more by focusing on applications related to heat transfer. Okay, so, you may have, let us say we had this problem of flow over a cylinder, I mean flow over a flat plate. So, in this problem the plate could be heated and this fluid could be cold, and you can ask how much is the energy transferred from the hot surface to the fluid. Similarly, cylinder could be hot, fluid could be cold, or of course, fluid could be hot, cylinder could be cold, and you could discuss energy exchange between the two. So, that is the class of problems we are now addressing through the energy equation. Okay. You can't do it with mass and momentum, because temperature becomes a dependent variable only in the energy equation. If you say temperature is constant, that itself is the solution of the energy equation. Okay. So, there is no need to solve an energy equation after that. So, in a heat transfer application, temperature as a function of position and time is the dependent variable. Okay. So, now what happens is, so in this definition of E equal to C T plus U square over 2 plus G Z. This part, so in a problem of this type, you have a hot surface and you have cold air going over it. The changes in the first term. So, how much would be the changes in the first term? It will be C times T h minus T c, that will be the change in the first term. Okay. So, this term is, in a colloquial manner, it is called thermal energy. This of course is kinetic energy, this is gravitational potential energy. And E is referred as total energy. So, in general, of course, you have to solve for small e, the distribution of small e. But in most applications, it turns out that changes in thermal energy numerically turn out to be much larger than changes in the kinetic energy and changes in the gravitational potential. Okay, so, this is a result I am giving you without really proving anything, but it turns out that way. Otherwise, of course, in some extreme cases, it may so happen that the other two terms are also significant, in which case you have to solve for E rather than temperature. So, if thermal energy is much greater than K E plus P E, then it is sufficient to retain C times T, and then the energy equation becomes Q dot equal to integral over C V Okay, I have put E equal to C T and I have set W s equal to 0. You can simplify it further by requiring, I mean as in the examples we have done earlier, let us set rho equal to constant, and we have also discussed problems where mu is constant, C is constant. So, C is also specific heat constant, specific heat. What are the units of small e? It would be meter per second whole square, which is the same as joule per kg. Okay. So, specific heat would be joule per kg K. Those are the units of specific heat. Okay. So, if these are constant, then Q dot will be equal to rho C integral over C V, the time derivative, plus d s. Okay. Now, to the surface integral, you can convert that into volume integral. That will give you del dot u t, but since we have set rho equal to constant, what is del dot u? What is del dot u if rho is constant? 0. Okay. Therefore, del dot u t will become, you can take temperature u out, and that will make it u dot gradient of T. So, writing the energy equation from a heat transfer perspective, where there are large changes in temperature, is equal to integral over C V rho C I think rho C can be taken out. So, this is the control volume, this is the unit outward drawn normal. So, what is the expression for Q? Okay. In the handbook approach, how did we specify Q? In the form of losses taking place in the tubes. Okay. So, in the global analysis, Q is prescribed from handbook information. In local analysis, what do? We have to introduce a material function. That is very similar to the stress strain rate relationship we had introduced for the momentum equation. So, Q dot first can be expressed as C s Q dot n d s, where Q is heat flux. The units of Q dot would be watts. So, the units of heat flux would be watts per meter square. Okay. Now, you have to recall the sign convention. Q dot n will be the heat flux along the outward drawn normal, which makes it negative. Okay. So, this is the expression for Q dot n. So, this is in terms of C V, it is del dot Q d V. and equating the two and requiring that CV is as yet unspecified, so we get, well, there is a negative sign. So, rho C Q is a heat flux vector. There is no difference between small q and large q, except that q is a local property. Capital Q is defined for the entire control volume. Okay. So, now the previous equation is defined on a global scale, at the scale of a control volume. This is now defined at a point. This is temperature at a point, temperature at a time instant. Velocity, how do you get velocity? Velocity should now come from the solution of mass and momentum equations. Okay. So, in a general problem, solve mass and momentum for velocity, put that velocity distribution into this equation and get temperature. Okay. So, this is a heat transfer perspective. This is a special solution of the energy equation, which gives you temperature. Okay. Otherwise, it gives you total energy, small e. So, now it remains to specify Q. Okay. You remember we had momentum equation where we had mass times acceleration equal to, we had surface forces and body forces. Surface forces were written as del dot sigma. Okay. We had del dot sigma over there, where sigma was specified through the stress strain rate relationship, and strain rate was connected to velocity. That was the development over there. So, you have to give a constitutive relationship for Q, that is a material function. Okay. In the absence of a material function, you have to give a device level prescription, which is handbooks. Now, a material function now this material function is material specific, okay. But then, like in the momentum equation, we said many commonly encountered materials follow a linear stress strain rate relationship. With that, we went for the Newtonian fluid approximation. Okay. Not that every fluid is Newtonian, but a very large proportion of fluids are Newtonian. Similarly, this material function for Q is material specific, but a very large number of commonly encountered solids and fluids exhibit a linear relationship between Q and the gradient of temperature. This is a vector relationship, a linear relationship between heat flux and the temperature gradient. The constant of proportionality is called, any idea? What is it called? Thermal conductivity. K is called thermal conductivity. Okay. So, assuming K is also a constant independent of, so it is a prescribed value, then the local form of the energy equation is written as rho c is equal to k del square T. So, in a general problem, I told you, you have a flat plate and plate is heated and you have flow over that surface, and you ask this question, how much of energy is transferred from the hot surface to the fluid. So, if you want to do it in an analytical framework, you have to solve energy equation, where velocity distribution has to come as a solution of the mass and momentum equations. Then you solve this problem. So, naturally you will require, so subject to initial and boundary conditions. Okay. So, suppose you have this problem, this is T c, this is T h. So, hot surface the boundary conditions would be, let us say x equal to 0, t equal to T c, y equal to 0, t is equal to T h. Now, you may expect that far away from the heated surface, it is the far field which is undisturbed. So, as y approaches infinity, t approaches T c. You may also expect that at time t equal to 0, the flow field is all cold. So, t is equal to T c. So, these are some examples of initial and boundary conditions you can prescribe to solve the energy equation for temperature distribution. Now, once you solve for temperature, you get the temperature distribution. What do you do with it? The original question was, how much is the energy transferred from the heated surface to the fluid? So, that comes again from the heat flux. So, like we had wall shear stress, we had stresses everywhere, but the force acting on the object was obtained from the wall shear stress and the wall normal stress, which is wall pressure. So, similarly, the heat flux will have to be evaluated at the wall. This is to be followed by the evaluation of the wall heat flux. Okay. So, we have an expression for q equal to minus k gradient of T that has to be evaluated at the wall. That means, the derivative of temperature has to be evaluated at the wall. Okay. So, on Friday we will look at solutions of the energy equation. So, we have 3 more classes. So, we look at solutions of the energy equation.